In this chemistry tutorial, we're going to look at the periodic table of elements. The first aim is to describe the structure of an atom and define what an element is. Then we need to describe how the periodic table is organized. And then we're going to explain how the periodic table developed over time. Now, imagine it was the mid-1600s, and you, being a scientist, are asked to find out what matter is made of. Now, bearing in mind that you had no idea what an atom was, you would have probably developed the following idea. All matter is composed of a mix of 4 elements, those elements being fire, earth, air, and water. Yes, believe it or not, I'm not talking about the history of Middle-earth, but actually Earth itself. In fact, scientists and philosophers at the time believed that materials are made of a substance called phlogiston. And philosophers and scientists believed that when you burnt materials, you released their phlogiston. Now, in the light of today's knowledge of atomic structure, we know this is absolute nonsense, but at the time this was actually seen as a credible theory. But if matter is not made of fire, earth, air and water, what is it made of? Well, I'm sure it will come as no surprise to you that matter is made from tiny building blocks called atoms. The word atom itself means indivisible, meaning that the material cannot be broken down into anything simpler. And chemists today use the nuclear model to describe atomic structure. There are also other models that detail how matter may be put together. For example, you may have heard of the string theory. But most chemistry observations do follow the nuclear model, and it's very easy to understand. So, what is it all about? Well, the nuclear model goes as follows. There are 3 types of particles that make up an atom. We call these particles subatomic particles. 2 of these particles can be found in the nucleus of an atom, the central point of an atom. These are called protons and neutrons. All the mass of an atom essentially comes from the nucleus, in other words, the balance of neutrons and protons. Surrounding the nucleus are things called shells, sometimes referred to as energy levels. And orbiting the nucleus within these shells are particles called electrons. Now, in terms of chemistry, I think it's fair to say electrons are the most interesting particles, as you'll see later. So it's absolutely essential as chemists that we get the basics right. In other words, understanding the properties of each subatomic particle, protons, electrons, and neutrons. If you forget, just remember the word pen. So first let's look at the relative mass of each particle. Protons have a relative mass of 1, as do neutrons. What this means, relative mass, is that the mass of a proton is equal to the mass of a neutron. Relatively, they are the same. However, relatively, electrons have a much lower mass. In fact, you can see that it's 1,836 times lighter than protons and neutrons. In some exams, this may be rounded up to 2,000 times lighter. The point is, the mass of an atom comes from the nucleus, from the protons and neutrons, not from the electrons. So if you wanted to work out the mass of this atom, you just count up the individual particles in the nucleus, 7 in total, 3 protons, 4 neutrons. Next is the idea of charge. Protons have a +1 charge, electrons have an equal and opposite charge of -1, and neutrons have no charge at all. Think of charge a bit like magnetism. 2 positives will repel each other, but positives and negatives will attract each other. That's really all you have to take from this idea of charge. Similarly, 2 electrons will also repel each other because they both carry a negative charge. So likes repel, opposites attract. And also, please remember that protons are found in the nucleus, neutrons are found in the nucleus, but electrons are found orbiting the nucleus in the shells. In an exam, you may get a table like this with certain parts missing, and you'll have to remember these details to fill them in, but it's easy marks. I mean, most of the numbers you have to memorize are 1 or 0, and you just need to remember plus or minus. So here are the key facts you should take from this. 1. An atom's mass is the mass of the nucleus. You just add the protons and the number of neutrons. So as I said, 3 protons plus 4 neutrons equals 7. So this atom has a mass of 7. Secondly, the nucleus has a positive charge, and that's because it contains protons which have a positive charge. The other particles are neutrons which have no charge, so the overall charge is positive. This nucleus in particular has a positive charge of 3 because it has 3 positively charged protons. Also very important, the overall charge of an atom is neutral, and that's because the number of protons with a positive charge equal the number of electrons with a negative charge. So you can see 3 protons in the nucleus and 3 electrons whizzing around the outside which have a negative charge. So even though electrons are much smaller in terms of mass, they still carry the same amount of charge, but in the opposite way, so negative as opposed to positive. So an atom that hasn't been tampered with will have a neutral overall charge, but if you do start playing around with it by adding or removing electrons, you will give that atom a charge. You could add more electrons, giving it a negative charge, and you could take away electrons, giving it a positive charge. Either way, you create an ion. An ion is a chemist's word for a charged atom. So today's lesson is on the periodic table of elements, but what are elements? You see, all materials are made of atoms, and some materials are elements, whereas others are compounds. What's the difference between these? Well, imagine you're about to eat this sandwich. The bread you're about to eat is not an element. It is a compound because it contains many elements chemically bonded together. In this case, carbon, hydrogen, and oxygen bonded together to make the compound carbohydrate. The water running through this tap, as you may have realized now, because I said initially water was thought to be one of the main 4 elements, we now know is a compound, not an element. Why is that? Well, every molecule of water is made from hydrogen and oxygen, so let's take a closer look. You can see every water molecule consists of an oxygen atom and 2 hydrogen atoms bonded together. I'm sure you can understand why water is referred to as the Mickey Mouse molecule. So a compound is when 2 or more elements are chemically bonded or chemically combined, chemically stuck together. So that's compounds, but there are about 118 materials that we've discovered in this universe, not just the Earth, that are made from one type of atom. These are called elements. So you can see this bar of gold is only made from gold atoms. The chemical symbol for gold is Au. If I was to break this gold bar down into smaller pieces, it would still only be made of gold atoms. We couldn't break it down into anything simpler. That is why gold is an element. Similarly, if we look inside this oxygen tank, we'll find the element oxygen. Now you can see the difference here. Oxygen I've shown to be bonded to another atom of oxygen. This does not make it a compound because we're still only dealing with one type of atom, but this does make it a molecule. So note that a molecule is when 2 or more atoms are chemically bonded together. Molecules can be compounds like carbohydrate and water, or they can be elements like oxygen. It depends on how many different types of elements they're made from. So think of elements like nature's building blocks. You couldn't break this down into anything other than a red Lego brick. So I could combine atoms together to make molecules, so now I've got a molecule of oxygen. Or I could combine different elements together to make a compound, so now I've got a compound of sulfur dioxide. Or I could do this and make nitrogen dioxide. So in this way you can literally see how atoms are like building blocks that we bond together to make more complex structures. The final point to make here is that the number of protons that an atom contains in its nucleus defines what that atom is. It's like its ID card. So if you have 8 protons in your nucleus, you will be the element oxygen. If you have 7 protons in your nucleus, you will be the element nitrogen, and 6 protons in your nucleus, you will be carbon. The number of neutrons in an atom can change, but that doesn't affect what you are. Only the proton number, or also referred to as the atomic number, determines what element you'll be. Today, we organize or arrange elements in order of their atomic number. So hydrogen's first with an atomic number of 1, for example. So now we can describe the structure of an atom by stating where we find each subatomic particle and their mass and their charge. And we can also explain what an element is. So aim 1 done. So now we're going to look at probably scientists' most useful contribution to chemistry, and that is the periodic table of elements, which was devised, or the modern version was devised by Dmitri Mendeleev. So the periodic table is truly amazing. It's almost verging on magical, quite frankly. It was able to predict the properties of undiscovered elements, but we'll look at that in a bit. So in this one, and bearing in mind that you'll find these periodic tables at the front of every chemistry exam paper, so you don't need to remember all this stuff, just understand how to read it. And admittedly, when you first look at it, it's overwhelming, but you just need to break it down, you'll see how simple it really is. Firstly, don't forget you're actually given a key with a periodic table. And that key tells you what each of these things means. So the top number is the atomic mass, the number of protons plus neutrons in the nucleus. Then we have the atomic symbol, which is either one capital letter So you can see V here, or it can be composed of two letters, the first one being capital and the second one being lowercase. For example, the element chlorine, which is quite a popular element to focus on in exams, has to be written with a capital C and a small l. The number of people I've seen write a capital L in an exam is a little bit concerning sometimes. So please remember, write a lowercase l. So just to test you understand, in this compound, how many elements do you see? Well, Ca denotes 1, so I'm going to isolate that one off. Then we have a capital C by itself, so that's another element, and a capital O by itself, so that's the third element. So we have 3 elements in this compound of calcium carbonate. Okay, so then we have the name of the actual chemical, so hydrogen here, and then finally the atomic number, also sometimes referred to as the proton number, because it tells you how many protons are in the nucleus, and it also tells you which element it actually is. So if you have a proton number of 1, you're going to be dealing with hydrogen. The proton number also tells you by default how many electrons are whizzing around in the shells around the nucleus. So for example, chromium has a proton number of 24, so it has 24 protons in its nucleus, but also 24 electrons outside its nucleus, because if you remember, I said there's no overall charge on an atom because the number of electrons and protons are always balanced. But by definition, if you just say, what does the atomic number tell you? It tells you the number of protons in the nucleus of an atom. Now you can see that the elements are organized in terms of their atomic number. So 1, 2, 3, 4 protons, 5 protons, etc., etc., etc. The mass doesn't go up in regular steps like the atomic number. Look, we go from 1 to 4 to 7 to 9 to 11 and so on. Also remember, from the atomic mass and the atomic number, we can work out the number of neutrons in an atom. This is something you also get asked in an exam. So fluorine has a mass of 19. That tells us it has 19 particles in its nucleus. And we know 9 of those particles are protons, because looking here, 19 atomic mass, 9 atomic number. So if it has 19 particles in its nucleus, and 9 of those are protons, 19 take away 9 gives you 10 neutrons. So just subtract the atomic number from the atomic mass to work out the number of neutrons. Okay, so let's start making sense of our table or organizing it. The first basic thing to organize is putting this little step ladder here. The step ladder starts above aluminium, so just remember A for above aluminium. And then steps just go down, 1 across, 1 down, 1 across, 1 down, and so on. Now, what this division line signifies is that on the left-hand side of the periodic table is where you'll find metals, elements which are metals, some which will be familiar to you, like copper and zinc and iron and so on. Whereas on the right-hand side of the table, we have non-metals. So again, some of these might be familiar to you, like oxygen and nitrogen and chlorine. But it doesn't stop there, we can carry on organizing it. So if we go to this shaded pink region, this highlights the most reactive metals in the periodic table. So these here in the first 2 columns are the most reactive metals. Then if we look at this big sort of rectangle of elements in the middle, and by the way, don't panic too much about learning these. You don't really need to know them all at all. You just need to know they're called the transition metals, and they can be identified because they can form colored compounds when they react. You see, anything outside of this rectangle, if it reacts, it will form normally a white or colorless compound, but here they form colored compounds. For example, copper sulfate is blue. Some lead compounds are yellow. Now, if we look here, we find the most reactive non-metals. These are called the halogens. And finally, we find the least reactive, kind of boring group of elements called the noble gases or the inert gases. But I'm sure you've also noticed their numbers on the periodic table. Now, in your exams, you'll get these numbers, but you will not get these numbers. So it's pretty easy to remember them. 1 goes parallel to hydrogen and helium, then just 2, 3, 4, 5, 6, 7, all the way down. But what do these mean? Well, these numbers are referred to the group number, and they basically apply to the vertical column below the number. So this is group 1, this is group 2. Notice how there are no group numbers for these transition metals, but then it resumes here, group 3, group 4, group 5, 6, 7, and the final group can be referred to as group 0, but is sometimes also referred to as group 8. So the group number tells you the number of electrons on the outer shell of an atom. So for example, this atom would be found in group 1 because it only has 1 electron on its outer shell, and you can see it there. Now that might be a weird thing to point out. Why is that even important? Well, pretty much all of chemical reactions depend on this. So the number of electrons in the outer shell is incredibly important, and it tells you how reactive an element is. And on the left-hand side, we have the period. Now remember, it's called the periodic table, so this is quite important as well. And what the period number tells you is the number of shells that surround the nucleus. So you can see, for example, this atom has one shell and then a second shell, so it must be in period 2. Now if you remember, I also said it's in group 1 because it has one electron in its outer shell. We can identify it from this table almost like playing battleships by using coordinates. We can see group 1, period 2, it must be lithium. So just to summarize, here we'll find the reactive metals in groups 1 and 2. In the middle, we find that rectangular block of elements called the transition metals, and they can be identified because they can form colored compounds. On the right hand side, we find the most reactive group of non-metals called the halogens, that's group 7. And then finally, we find the noble gases or the inert gases, which are basically very boring, lazy elements which don't react whatsoever. Now you can earn a lot of marks in the paper just by understanding the periodic table. I have done another tutorial which goes into this in more depth, so you can really take some shortcuts and get marks very quickly in an exam, but you can watch that at another point. So that's how we describe how the periodic table is organized. Aim 2. So now let's look at the history of how the periodic table developed. Well, in the 1800s, we didn't really know much about atomic structure, so we just could weigh the same volume of different elements and we could put them in order of their atomic mass. So hydrogen would be the simplest, and then in this list, for example, carbon was 12 times heavier than hydrogen. That's why it has a relative mass of 12, and hydrogen has a relative mass of 1. Then chlorine here, then iron here, for example. So it was fairly easy to do to organize elements in terms of their mass. And here's the part that blows me away every time. A pattern was noticed when they did this. So here we have elements arranged in order of their mass, and what chemists noticed is that periodically they would get a repetition of properties. So for example, here is lithium. Now lithium's a very reactive metal. It reacts quite violently in water. But then as you move along, you find elements which don't do this, but then again we get another metal which does exactly the same thing. And here again, if we look at this element, this is fluorine. Fluorine is a non-metal which forms poisonous coloured vapours, and if we move along, nothing, then once again we get a repeat of those properties. Chlorine again is a non-metal, and it also produces coloured poisonous vapours. So the pattern seems to be repeating itself every 7 elements. In today's modern periodic table, we now know it's 8 elements, but one entire group, group 8, had not been discovered yet, so something should have gone in between these two. So in 1869, Dmitri Mendeleev had this genius idea of organizing the 50 known elements according to their property. He did this by observing how elements react in certain conditions. In other words, how if you heat them in oxygen, do they form an oxide? If you react them in water, are they very reactive? He looked at compounds, their colors, all sorts of different properties. And he ultimately realized that if you make a snip in this line and then place this sort of row of elements underneath, then suddenly you have elements with similar properties in the same group. But he also left gaps in his periodic table. He came up with the idea that not all the elements in the universe had been discovered yet. And what troubled him was the idea that here you have a lot of elements with the same sort of chemical properties, but you have a couple which just don't fit the rest of the group. He was so disturbed by this that he really thought that, no, there must be something else missing. We haven't discovered this element. So he shifted some of these along to create gaps, confident in the idea that some elements haven't been discovered, and when they are discovered, they will fit nice and neatly into these gaps. This is what I mean by the periodic table had the ability to predict undiscovered elements. And what's completely freaky is he was completely right. Just through devising this crazy table, he was able to predict undiscovered elements. We now know that gallium and germanium are found here, and they do share properties with other elements in their group. At the time, his idea was seen as very arrogant and upset a lot of other chemists, but he stuck to his guns, and with good reason. So it's a very common exam question: why did Mendeleev leave gaps in his periodic table? And here's what you would say: some elements did not share properties with others in their group. There must be undiscovered elements that do share these properties. And remember, group 8 or group 0 was discovered much later. And there's good reason for that. They're not reactive, they're colourless gases, they're very hard to notice. When you're training to become a teacher, they tell you always focus on the children who are very quiet. All the loud ones get all the attention, but you've got to notice what's happening with the quiet one. And I think that's pretty analogous to what happened here. Okay, so that is how the periodic table developed over time. And that's aim 3 done.